So we've talked about measures of central tendency, the mean, the median, and the mode. And then we talked about measures of dispersion, which was the variance, the standard deviation, and the range. Now we're going to talk about measures of position. Measures of position describe the relative position of a certain data value within the entire data set. So one of those is what we call a z-score. And a z-score represents the number of standard deviations a data value is away from the mean. So the equations for finding z-scores for both the population and the sample are given below. They're the exact same formula. It's always the data value. So X is the data value. And the mean or the X bar, the mu or the X bar, that's the mean. Remember, we're just using the population mean versus a sample mean. S is the sample standard deviation. And remember, sigma is the population standard deviation. If the data value is less than the mean, in other words, if it's to the left when we graph it, then the z-score is negative. If the data value is greater than the mean, then our z-score is going to be positive. So I'm going to flip over to another page here. This is just blank paper. And we're going to draw the graphs, a normal curve with the z-scores labeled in here. So here's our regular normal curve. Remember, the mean is right in the middle. The corresponding z-score is 0. Because remember, a z-score is the number of standard deviations we are away from the mean. So if we're at the mean, we haven't gone anywhere away from it, so we're 0 away from it. Okay, going to the right, remember we add a standard deviation. So this is the mean plus 1 standard deviation, the mean plus 2 standard deviations, and the mean plus 3 standard deviations. The z-scores that go with that, well, at 1 standard deviation away, and a z-score is a standard deviation, so z is 1. Then we have z is 2, and z is 3. So similarly, going to the left, remember we subtract standard deviations. And so the corresponding z-scores for those are negative. So if we're 1 standard deviation below the mean, our z-scores are negative 1. 2 standard deviations below, z is negative 2. And at 3 standard deviations, z is at negative 3. And of course, it can be any number in between those, and it keeps going forever. So z can be any number. Okay, now that we've seen how z-scores relate to our normal curve and the standard deviations, let's go back and try a couple problems. So determine whether the LA Angels or the Colorado Rockies had a relatively better run-producing season. The Angels scored 773 runs and play in the American League, where the mean number of runs scored was 677.4 and the standard deviation was 51.7 runs. The Rockies scored 755 runs and they play in the National League, where the mean number of runs scored was 640.0 and the standard deviation was 55.9 runs. So we want to compare things using z-scores when they're in different groups that have different means and standard deviations. So remember, I'm sure most of you had a elementary school math teacher sometime that said you can't compare apples and oranges. Well, with a z-score you can. So you can't directly compare two things that are from different samples or populations without comparing their z-scores, which just compares how they did relative to everybody in their group. So let's just do the calculation. So for the Angels, the z-score is the data value minus the mean divided by the standard deviation. And I'm using the population notation here because we're talking about every single run in the whole season. So that's a population. So they scored 773 runs. The mean number of scores for the American League was 677.4, sorry, of runs, not scores. And the standard deviation was 51.7. So if we put that in the calculator, 773 minus 677.4. Remember, before we can do the division, we need to hit enter on the keypad. And that's because of the order of operations. Then we have to divide by 51.7. So that gives us 1.85. So a note here, we always round z-scores to 2 decimal places, and that's just by convention. Back in the old days before technology, we had to convert everything to z-scores and look things up in tables. Technology has prevented that, so you won't get the pleasure. Well, it hasn't prevented it, but it's made it wholly unnecessary. So this 1.85 says that the Angels' number of runs is 1.85 standard deviations above the mean number of runs for their league. Let's do the same thing now for the Rockies. So for the Rockies, they had 755 runs. And for the National League, the mean was 640.0 and the standard deviation was 55.9. So again, if we do the math, 755 minus 640, enter, divide by 55.9, we get a z-score of 2.06. So if we draw a little picture here, here's the mean, which is a z-score of 0, remember. And we have 1, 2, 3, and -1, -2, -3. So the angels is 1.85. So that's the angels. And the Rockies are at 2.06. So they're right there maybe. So who scored relatively better? The Rockies had a relatively, because we can really only compare them to their group, relatively better run producing season than the Angels. Because their number of runs was more standard deviations above the mean. In other words, they had a higher z-score. Now, you can't always assume that the bigger z-score is the better z-score. It depends on the context of the problem, and we will look at a problem where it's different in the next video.